Good afternoon, everyone. Now we'll discuss about the design thinking topic of directional couplers. So let us see the design thinking stages of empathy, define, ideate, prototype, and testing. Now Jia will explain the problem statement.
Yeah, I would like to share about the problem statement. It is about direction of the movement of static objects for security purpose, such as to protect indoor areas and locations where important assets are located, such as museums or libraries, or in automotive to avoid car collisions. An alarm can be triggered by any of the reflected waves caused by a moving object or by any movement of an object with a radar cross section, which is shortly known as RCS, larger than a threshold. Example, to detect humans but prevent the detection of noise.
The empathy part of this problem statement is understanding the needs of engineers and users. In order to achieve tight coupling and high electricity compared to the standard coupled line directional coupler in an X frequency band using low cost material and technology. However, the improvements is not straightforward since increasing the coupling factor using low cost material in a far higher frequency range, where dielectric and ohmic losses could be critical, can be challenging. We can apply asymmetric cadence connection to two coupled line sections. Configuring is able to strengthen the coupling factor over that of a SEs with the same interline spacing. The aim of the motion detection system is the detection of the movement of scattering objects. The detection of a movement usually triggers an alarm or more generally activates other electronic subsystems.
So let's move to the define part. Define the goals and objectives of the directional coupler design. So coupled line coupler based on asymmetric cascade connection of two coupled line sections is used to achieve a high coupling factor using low cost material and technology. The proposed coupler can be effectively used in Doppler motion detection sensor using to its strong coupling and relatively high isolation.
So now ideate parts for improving directional couplers. The microwave parts of a MDS is mid-wave voltage controlled oscillator, a low pass filter, a transmitting and a receiving antenna, a mixer and a directional coupler. The directional coupler is required to perform a coherent detection of the received signal, thus allowing the larger receiver sensitivity and then larger detection range. Thus, this coupler requires both strong coupling and a large isolation. On the other hand, it should be compact and low cost. As such, the directional coupler is one of the most critical component of the microwave MDS.
In prototype, focus on the design of the directional coupler employed to feed the mixer of the Doppler motion detection sensor. It is a volumetric band microwave sensor using the Doppler effect and digital signal processing for external protection. Like all sensors using microwave technology to detect motion, it exploits the principle of a Doppler radar where a continuous wave of microwave radiation is emitted by a RF source. The frequency shift in the reflected waves due to the motion of an object toward the receiver results in a signal at low frequency.
So now after knowing about all the stages, now we get into testing. So this performance is then enhanced by subsequent signal processing, which after amplification is digitalized using an analog and a digital converter. This digital signal is handled in real time by the onboard microprocessor. Using appropriate algorithm, it is possible to measure the distance and the mass of the object moving within the detection areas, analyzing all the received data using a fuzzy logic. Then, the testing of coupler design is the proposed coupler can be used in many different microwave systems. However, in order to experimentally access the proposal to realize and test a coupler to be used in expand DMDS, the requirements are therefore a strong coupling between the through line and the coupling port over the bandwidth of 10 to 11 GHz using a low cost PCB and process. The organic ceramic laminated with ER equal to 3.5 and tan alpha is equal to 0.003. The dielectric slab thickness was 0.762 millimeter and the copper thickness was 35 meter. The smallest spacing available on the PCB with the standard, that means the cheap process, was 0.15 millimeter. And this value was used for the gap between the coupled lines.
Thank you all.
Thank you.
Thank you.